Okay, let's go for section 5. Okay, on chapter 1. The size and proper properties of the fat belt and its associated pull legs anyway. For 5.1 is going to be size and properties of the flat belt, things like that. That what I just talked about it already. So therefore, we're going to go down for the design of the flat belt and its associated parts anyway. So therefore, let's see on that. We're gonna set here size and some properties of the most common flat belt based on the ISO standards can be selected for the design of the belt drive transmission. Let's see one the table 1-2 to one table 1-4 illustrate the most common flat belt size for the ISO standards. Okay, let's go for it. Set here. Okay, in table 1-2, okay, you may figure out this is gonna be the belt width. It's gonna be small p, and the pulley width is gonna be the capital B left respectively. Okay, you may figure out, see the pulley, okay, the belt's gonna sit on the pulley itself. So therefore, the pulley is rather bigger, okay? The width of the pulley gonna be bigger or greater than the size of the belt width anyway. So for instance, see, if you go for the first line there, it's in millimeters. The small b is going 16, and the capital B is gonna be 20 respectively. So that to allow the belt to sit properly on the pulley width anyway. So therefore, this is going to be the standard that what we're going to apply for for the fat belt anyway. Okay, and then therefore, okay, we can make selection. This mean this is the most common fat belt width anyway. So for the first column here, we're going to think about this. Anyway, the availability is going to be 16, chapter 20, and 25 up to this one, up to 500 millimeters width anyway for the belt that been available. You can go shopping for the fat belt, things like that in the market, whatever. So therefore, another one is going to be more fat belt length. Okay, it's going to be sold in the some kind of like a millimeter or in inch, whatever. But typically now it's going to be SI units. It's going to be in inch, most typically. So therefore, it's going to be sold. The fat belt length is going to be up to 500, up to 2,500, things like that. So this is what you're going to consider about to buy it. As long as possible, and then you just maybe you can cut it to be ever you want to, things like that. Okay, so therefore that 4 is going to be belt width and its corresponding number of belt ply. Okay, let me explain about the plies here. Okay, the plies mean we can make like some kind of like a rubber impregnated. Okay, some typically we're gonna apply something like a fiber or some kind of like a belt match, things like that, together to be steel, ion steel, things like that. Okay, match, things like that to be the one applied. It means the first ply gonna comply with the cord or some kind of like fabrics, okay, and then impregnate with the rubber. We call it one ply. And then if we just apply for more ply, things like that, we can do the same manners to put everything down. The number of applies you it means you're gonna pay more money to apply for it, and also of course, right? If you got more number of applies, it means you got more strength, okay, more power to be generated, things like that. So this is the thing that what we're gonna consider about it. Okay, we're gonna do the optimum design with the number of applies. And typically, you see, it's going to be the minimum plies of the flat belt is going to get started from number three plies up to whatever 12 plies is available. But it's corresponding with the belt width anyway. You may figure out, see, this is in millimeters all the way, okay, and then the minimum number of plies being available up to 3 to 5, things like that. Well, mostly things like that, okay. And then for the flat belt pulleys, okay, that what this is the pulley here is typically made of cast iron. Okay, this one it's been cast already. So therefore, this one is going to be the crown. That what we put down here. The crown is going to be the parts of the pulley to allow the belt going to sit on the top there. This is going to be curved all the way to allow the belt to be sit in proper manner, things like that, to avoid the belt to be loosened, to avoid the belt to run away from the pulley, things like that. Okay, so typically for the fat belt, we're going to crown it, look like that. Okay, so this is going to be that what I said here, a fat belt pulley or cloud pulley, things like that. Okay. And then, okay, table 1.5 is gonna be fat belt pulley diameter and screwing crown height, things like that. This is gonna be manufactured, look like that. Okay, so therefore, for example, the pulley diameter is gonna start from 40 up to 112, things like that. Okay, it's got a crown height. It's gonna be manufactured with the crown height 0.3. It's been being designed already by the corresponding manufacturers, things like that. Okay. And then 1.6 you're gonna get for the crowd height, okay, and for the for 400 up to 200, okay, 2000 millimeter, okay, for the pulley diameter. It's gonna be the same thing. So this is the design, okay, that what I recommend on it. Okay, the belt width. It's gonna get started, okay, with the first line there, okay, combination with the pulley diameters there, okay, this one, okay, so that's why you can have a look at the crowd. I recommend it to be follow up with the table 1.6 respectively. And then for the recommended referral speed of the metro made, okay, and then fat belt pulley. It's very important, okay, because that's why one of big concern is going to be metro. It's going to be in terms of the coefficient of friction, of course, right? So for the cast iron, that what I mentioned earlier, typically, the fat belt type gonna use together with the crown pulley or the cast iron pulley, things like that. Typically, the crown pulley is made of cast iron, so therefore, it's gonna be the first line. It's recommended to be 18 to 23 meter per second. Okay, for the mice, you're gonna be better. Okay, high speed, things like that. If woods, of course, you're gonna have much more, okay, coefficient of friction, so therefore you can run for at the higher speed. And rim part of the wood, things like that, okay, you can apply the wood on the rim, things like that, to cause more friction, whatever. And then pressed paper or fiberglass, things like that, it's going to be run with the higher speed, things like that. Okay, this is the thing that what we basically recommended the speed that follow up with the coefficient of friction or the mattress of the pulley itself. And then 1.8 is going to be most common fat belt diameter is going to be available. Okay, this is the pulley diameter available. So this one, see, you can figure out in the corresponding availabilities of the nominal diameters that were available. Okay, so typically you're gonna use this kind of thing as the things that what you're gonna go for is gonna be nominal diameters in a way. It have a maximum and minimum respectively. Okay, so therefore this is the availabilities of the pulley in the market. You can go shopping for it. Okay, so let's go for uh, more details of this is gonna be in terms of the design, okay, the fat belt drive transmission. The first thing first, we're gonna go for the collected power. The collected power is mean, okay, this is gonna be include the slippage, okay, the lost, okay, and everything powers already between the driving shaft and the driven shaft respectively. So therefore, this kind of thing can be made to calculate for the P term. It's going to be the real power that what we need. We call it collected power. And then transmitted power is going to be U sub P respectively. And N sub S is going to be service factor. It's going to be between from table 1.9 and N sub A is the out contact correction factor. This means from table 1.10 up to 11 respectively. Okay, so that's what it said here. This is going to be important here. I would like to read it out for you guys. Typically, the corrected power is greater than the transmitted power, W sub P, in order to allow to obtain higher strength or compensate the associated losses anyway. what I mentioned. See, we have mechanical engineering, things like that. So therefore, a lot of laws is involved with the operation of the everything, so anyway, in the mechanical sense, things like that. So therefore, we need for the transmission power, but of course, the real power got to be greater to just provide for the losses associated, things like that too. Okay, and then for the next thing that what we're going to design for the belt width, be here. That what we're gonna go shopping and then make some kind of standard belt that what available there. This means from the 25 times P after we got a calculation of P already, correct power, and then we got to find another term is P sub O. Okay, P sub O stands for power being transmitted. They just use as a 25 millimeter width of the fat belt as a standard. Okay, as a reference level anyway. So other than 25, we're gonna convert to have a correlation with 25. So therefore, we have a power, okay, corresponding at the 25 millimeter width of the fat bed wheel drive anyway. It's going to be P sub or can be given from table 1.14 respectively. Okay, so I explained the weight, okay, per units up to 25, okay, already. It's going to be determined from table 1.12, okay, and then the minimum pulley size of the fat belt drive, okay, that what we can determine from the table 1.13. Okay, we're going to go for it one by one then. Let's go for table 1.9 service factor, okay, and service. So I would like to recommend you guys to think about the service factor. What does it mean by service factor? Service factor is not a safety factor, of course. Service factor is mean, okay, if the system of the driving is good, okay, you got very good service factor, okay. If you get the poor system of the driving system, things like NSAP is going to be down low, things like that. So therefore, all the associated parts or associated transmission manner, things like that, got to be involved. For instance, like the driven apparatus. Okay, for instance, like you have a motor as a prime mover and the driven part as a pump, things like that. Driven apparatus is going to be the pump, and then we consider about the prime mover itself. Okay, the prime mover is going to be the driving units. Okay, the engine, things like that, motor, electrical motor, whatever. Prime mover does it mean here? Okay, we just make some kind of like differentiation for the prime mover to be AC, electrical motor, okay, with the normal torque and the high speed torque, right? You guys have studied on the basic electrical engineering course already, right? You can understand about the normal torque and the high torque with the typically power shoot, induction, things like that, okay? So therefore, typically, okay, we're gonna go for the normal torque typically, okay? And then for the DC electrical motor, things like that, we have a shunt wound and then three wounded, things like that, okay? You guys think about it, okay? And then for the ICE, see, for the speed, it's gonna be greater than 600, and then the speed is less than 600, things like that, okay? So this is the engine. Typically, see, you may figure out, okay, for the ICE, things like that, the engine typically just go for the 600. It's gonna be some kind of like a automotive parts, things like that. Okay, but for the normal in the industry, things like that, typically gonna be less than 600, things like that. Okay, and shaft transmission for the clutch and brake, things like that, equipped with the ICE, things like that. Okay, it's gonna be in this column, of course. Okay, and the working day, okay, working hours per day, things like that, less than 10 hours and greater than 10 hours, things like that. Okay, we're going to consider about it. But now in Thailand, see, it's going to be to ship anyway, less than 10 and greater than 10, things like that. But now we just most likely to make a ship of the workforce to be in 3 ships anyway. Okay, so therefore, okay, let's go for this. Let's consider about 2 ships in a way, just grade less than 10 hours a day or greater than 10 hours a day. And then we just make some kind of in more detail. We start with 85% initial drive, things like that, and then start with the direct drive. So most of the things, okay, you are mechanical engineering, right? You just mentioned about the flywheel, things like that. See, we just need the flywheel to make some kind of like a four-wheel linkages. Anyway, I'm sorry, four bar linkages, things like that. Okay, for the stoppage, things like that. So therefore, we just put the flywheel in order to run consequently, things like that, for continuously, things like that. So therefore, we typically put in the 85 percentage initial drive, things like that. Okay, and then if you put a direct drive now, you're gonna cause a lot of torque, things like that. But the new engine now, new engine, new equipment now, you gonna get started with direct drive already. Okay, so this one is gonna be in details. Okay, that what we gonna make a selection for either both. See, for the driving apparatus and the driven apparatus and the prime mover. Okay, and then not like that anymore. So that's why we're gonna talk in more detail about the light to jet to moderate duty. Okay, so this one is going to be really light or moderate duty for the driving system, things like that. For instance, like the fluid mixture, not a lot of impact. So everything is going to run very smooth, things like that. For a heavy duty, see, it's got a lot of impact, a lot of contact to the things like that, a lot of chop load applied on it, things like that. See, the briquette and bracket, elevator, rock crusher, things like that, and compressor, hammer mills, paper mill, things like that. See, this kind of thing is going to cause a lot of impact, okay, a lot of vibration, a lot of shock load, things like that, apply the system, whatever, okay. So therefore, 1.10 is going to be another table that determines for the N sub A. Okay, N sub A is going to be the arc of contact, okay, or correction factor between the wheel drive transmission. Okay, the first column is going to be differentiation between the capital D and small d then, okay, and then you got to find the center distance accordingly to find the N sub A in this column. So it means, okay, this table, 1.10, if you know the diameter of the driving pulley and the driven pulley respectively, you can use this kind of table 1.10 respectively. Okay, this is going to be N sub A. N sub A is going to be the out contact correction factor. And then if you don't know about the capital D and small d, but you know, right, arc of contact ends up A for the braiding system for the angle of contact. Okay, the angle of contact. If you know about it, you can just have a look at it for the correction factors of N sub A respectively. Okay, so N sub A is going to be determined for the alpha, that what you have got there. Okay, and then another one, if the F sub C, okay, the weight itself, okay, and the number applied itself, okay, typically 3, we're gonna have the weight per unit length, okay, Newton per 25 millimeter width of the wide, okay, the flat belt, things like that, okay, and then the minimum plies that what available, okay, for the pulley diameter corresponding. Okay, we're gonna have, if we shoot 3 plies, this better recommend the pulley diameter is gonna be 80, and then 4 ply, okay, gonna be 250 millimeters respectively. 3, 4, 5, and 6 respectively. Okay, and then 1.14, okay, we're gonna talk about a P sub or okay corrected power rather than 25 wide fat belt. Now, what I mentioned already, right? Remember that? Okay, we gonna make some kind of like a reference to the 25 millimeter width, okay, of the fat belt type, and the standard as a reference, things like that, okay. So therefore, you may figure out, see, we get start the first column from the number of lights. If we just design for the 3 plights, okay, we're gonna use these kind of barriers, okay. If we use the 4 plights, okay, if we use the 5 plights, we're gonna go for 5, 6, things like that, okay. And then the second column corresponding column is going to be speed, okay, the fatter speed, okay. either on the small pulley, okay? So typically the fastest speed is gonna be on the pulley shaft, okay? Small pulley is going to be driving units. And then the small pulley diameters here, okay? The fastest, okay, speed, okay, that's what we got there. And the small pulley that we got there, okay, we got to have the N P sub O respectively, okay? All right, we're ready to go for in just details for the example 1.1. Okay, 1.1 is going to go for an open drive fat belt transmission comprised of the driving pulley in a diameter of 315 millimeters and a driven pulley in a diameter of 800. So a small pulley is going to be 315 and then the driven pulley is going to be 800 millimeters. The center distance of the driving and the reading shaft is manipulated to be 1000 millimeters. The maximum power of the belt transmission is found to be 20 kilowatts. Given that the coefficient of friction between the pulley and the belt is the mu equal to 0.3, and the driving pulley is going to be 1500. To mean the minimum initial tensile force exerted by the belt needed to be installed. Okay, all right, let's go for it. This is going to be open drive, right? So therefore, the everything is going to be signed down under the formulations of the belt drive. Okay, open drive. Let's go for alpha 1. Okay, we take a formulation out and then we make substitution for the capital D and small d. Okay, and then C. Okay, we just got alpha 1 in radian, alpha 2 in radian respectively. Since, okay, alpha 2 is greater than alpha 1, the slippage may just take place at small pulleys, mean for the driving units. Therefore, the friction equation just used to be, we make a selection of F1 over F2 over E times mu times alpha 1 when alpha is greater than alpha 2 is greater than alpha 1. To make substitution, we got a relationship of F1 is so 2.5 something times F2 for equation 1 respectively. And then we're gonna go design for the small pulley. So that's why let's find the V belt. Okay, velocity. The velocity can be determined from pi d n1. We make a substitution there. We got V already, and then we got a W sub P. Okay, F1 minus F2 times V. We just make substitution. We got equation 2. Right? Equation 1 and 2, we got two unknowns, two equations. We solve it out. We got F1 is 1672 Newton, and then F2 is going to be 661.4 respectively. And then therefore the F sub I is going to be the means of F1 plus F2, okay, going to be the answer, okay. And then for the 1.2 again, I would like to go over it. An open drive fat belt transmission comprised of the driving pulley in a diameter of 200 millimeter and the driven pulley is of 300. The center distance is 1 millimeter. The driving pulley, is driven by an ICE engine at the speed of 1,500, right? So therefore, the prime mover is the ICE with a speed of greater than 600, right? So the power is transmitted to the belt and the driving pulley, which is directly connected to drive the air blower and mechanical dryers. Okay, so therefore it means the driven apparatus is going to be air blower anyway, and then the working hour is 8 hours a day, and then the transmitted power is going to be 10 kilowatts. Okay, we're going to determine the size of the fat belts anyway. Okay, let's go for it. Since the driven pulley is got mechanical dryers, okay, so therefore it's turned out to be the light to moderate duty, okay, based on the table. Things that what we've got there, okay, let's see. For that, remember that we have this one, right? Okay, mechanical dryer, right? Air compressor, okay, okay, air compressor, right? So this one, oh, I'm sorry. This is gonna be mechanical dryers. You see it, light to moderate duty. Okay, and then remember we have less than 8 hours. Okay, so therefore we're gonna go for this one. Okay, less than 8 hour, and then we have the ICE, right? It's gonna be greater than 600. So therefore this come in 1.0 up to 1.2. Okay, and then therefore we just we just right, okay, you said here the primary IC is greater than 600. Okay, assume this start to be the direct drive. Okay, this one that what I talked to you down already. Nowadays the most of the machinery gotta be direct drive rather than the put on the initial drive, things like that. So therefore, being another figure 1.9 ago, a way ago, we got the n sub s is 1.2. The center distance, okay, we have d capital D minus d, the small d is going to be 400, and the center distance is 1. So 1 table point 10, the arc of contact just from table 10 dash 1 dash 10. Okay, we got the n sub a respectively. So we find the collected power, okay, automatically put on this formulation. So therefore we just design with the minimum bell points, okay, with 3, and n1 is going to manipulate to be 1500 already. So therefore, based on table 1.14, okay, we got the p sub o turn out to be 3.49. Okay, you gonna have a look at it, and then the b, okay, can be to me now. Okay, the width of b is going to be 93.4, and let's go for the availability from table 1.2. We got to make the sequences. Okay, the what available. Okay, 93. That's why we make calculations. That's why we go shopping. We make a selection on the B3 100. Okay, and then check on table 1.4. It's found that the number applied the fat bell with B is 100 is 3 up to 6. Therefore, the list of the applied of 3 applied is within the range. So the selection of B is 100 is okay. Okay, now we just great confidence that okay, the our design is correct. It's already. So that's why we just go through the rest of that. Vitamin of alpha 1, okay, alpha 2, right? And then the belt length, things like that, okay? And then therefore we got everything now to be fully answered and fully installed for the mechanics, things like that, okay? So I stop it for a while, and next we're gonna go for the rebuild design. Okay, after this, anyway. Okay.